Before we start to modify our data model, let's just take a look at two options that we have for specifying the characteristics of our data model to IFCore. One approach is to use the Fluent API that IFCore provides us with, and another is to use data annotations, which is the same approach that is used, for example, in ASP.NET MVC. For example, if we want to make it mandatory to fill out a text field in a form, we can use the required attribute, which IFCore also recognizes and uses to infer that a field in the database must not be nullable. In IFCore, the Model Builder class acts as a Fluent API, and as you probably know, we can access the Model Builder by overriding the onModelCreating method in the IFCore DB_context class. Don't worry if you're not too familiar with using IFCore's Fluent notation. We'll take a closer look at this during the next demo. A word of caution on using the Fluent notation is that it can be somewhat complex at first, but once you get the hang of it, it comes with a lot of advantages compared to using data annotations. For one thing, it helps keep our entity classes clean of implementation logic. Rather than crowding them with a lot of details which are actually specific to the database, we centralize these implementation details in the DB context where they'll coexist with other logic that defines how our database will be inferred. The flip side of this is, however, that our database context may easily become very crowded, so it's very important to keep a good structure in this class to make sure that it is easy to debug and update the code. The Fluent API also exposes a larger feature set than what is available using data annotations, and it can be used to set up a wide array of details regarding our entity classes, such as granular setup of relationships, mapping inheritance, and several other features that are not available using data annotations. Also worth noting is that the Fluent API allows us to work on classes that we might not otherwise be able to modify. For example, if they are being worked on by a different team or are defined in a library that we simply do not have access to modify. Data annotations, on the other hand, use the .NET attribute notation to specify characteristics of our entity classes. They are very easy to use, and for simple data models we can come a long way sticking to using these. They do have a tendency to clutter up our entity classes, and using them means that we'll put business logic inside our entity classes, which might not be the ideal way of doing things. It also means that this business logic will be distributed across several classes, whereas using the Fluent API allows us to keep this logic in one place. Also, data annotations expose us to a more limited feature set than the Fluent API. And they only work when we have direct control over the entity classes, meaning that we're able to and allowed to modify them. While the above list may seem to favor the Fluent API, this is not a case of either or. The two approaches can work seamlessly together and can be used to complement each other. Often we might want to start out simple, such as, for an example, imposing some restrictions on our data model, such as when fields are required, what is the max length of a field, and so on, which can be easily handled using data annotations. And later on we might need to work with relationships and other more complex setup things for which the Fluent API is more suitable. Throughout this course we'll primarily be using the Fluent API, but in the upcoming demo we'll take a look at a few examples of using data annotations. So in this demo we'll look at how we can modify how IFCore infers our data model to make sure that we get the database configuration that we desire. We'll look at how to set up such field-specific things as which fields are required fields, the max length of a string field, the precision of a decimal field, and the column type of a field. We'll achieve all of this using data annotations. As you can see, we are now back inside Visual Studio. And as we'll soon see, the development team at Carved Rock have made some changes to the data model that we just looked at. If we start off by looking at the customer class, we can see that all the properties that we saw here last time still exist, but a new one has been added called fullName, which simply returns the combination of the first and the last name. We can also see that a checksum property has been added, which is decorated with an attribute called NotMapped. Neither of these two properties will be mapped to the database, but for different reasons. The fullName property will be skipped because it does not have a set accessor defined, and the checksum property will be skipped because of the NotMapped attribute. This attribute is an example of how we can use attributes to control how IFCore infers our data model. You should note that in IFCore terminology, attributes are equivalent to the data annotations that we saw on the slides. If we look at the first and last name properties and the username property, we can see that these have also been decorated with attributes. In their case, they have had two attributes applied to them: the required attribute and the max length attribute. The required attribute means that the properties decorated with this attribute will be created as non-nullable columns in the database. Remember that because we disabled nullable reference types, IFCore defaults to making strings nullable. We can avoid this by using the required attribute. The max length attribute is also an example of an attribute that can be highly relevant to apply to a string property. In our case, we set the max length to 50 for the 3 name attributes, which will cause their respective columns to be created as nvarchars with size 50 in the database. It is worth noting here that the nvarchar type is a SQL Server type, and on different databases other types may be used to represent strings. Likewise for the length property on the nvarchar, which does not apply to all databases. SQLite, for example, expresses strings as the text type, which is always variable length. Now let's take a look at the item class. Here we see that, like we saw with the name properties in the customer class, item's description property has been decorated with the required and the max length attributes. This time max length is set to 255, which will lead to description becoming an nvarchar with size 255 in the database. If we take a look at the price and weight properties, we can see a couple of other attributes in action. The first one is the column attribute. If we look here in the Server Explorer, we can see that the price and weight columns are named exactly the same as their corresponding properties. If we would like to change that, we can do so by using the column attribute. In our case, we used the column attribute to change the names of the price and the weight columns to unit price and unit weight respectively. Also note that we use the type name property, which can be used to force a type on a column. In our case, we set up the price to be a decimal with precision 22 and scale 2. If we look at the properties for this column in the Server Explorer, we can see that EF-Core defaulted to making it a decimal with precision 18 and scale 2. If for some reason we want a larger number, since we have exorbitant prices, we can use the type name annotation to change the data type, as we do here. If we now look at the weight column, we can see that it is created as a real type on the database. This may seem surprising since we have defined weight as a float type, but in fact, real corresponds to a floating point type with precision 24. If for some reason we need larger values than the real supports, heavy stuff indeed, we can use the type name attribute to change the default behavior so that this column is created as a float instead, with for an example precision 36 as we see here. And lastly, let's look at the order class. Here we have simply decorated the name property with the required and the max length attributes to make sure that the column is created as a non-nullable nvarchar with size 50. Now let's try to apply these changes to the database. First we'll create a new migration by typing in add migration annotations in the package manager console. If we hit enter, EF-Core creates a new migration for us called annotations. As we can see in this file, it's all about modifying tables that we've already created in the database. First, we rename the weight and the price columns of the items table to unit weight and unit price, and then we define the database types for them, setting description to be nvarchar 255 and making it non-nullable. Also notice here that the migration file shows us the old database type, and also the old GLR type if we had changed that. And now let's have a look here where we define unit weight as a float with precision 36, and unit price as a decimal with precision 22 and scale 2. And here we can see that in the orders table, we set the name column to be nvarchar 50 and non-nullable. And lastly, in the customers table, we set all the name columns to be nvarchar 50 and non-nullable. If we now run update database in the package manager console, we apply these changes to the database. Let's look at the columns that we've modified to make sure that they match our expectations. If we look in the Server Explorer and take a look at the customers table, we can try to check out the properties for the first name column. If we do so, we see that it is now non-nullable and has length 50, whereas it used to be nullable and have a length equal to the max value. Likewise for the last name and username columns. If we take a look at the items table, we can see that the price and weight columns have been renamed to unit price and unit weight respectively. We can also see that unit price is now a decimal field with precision 22 and scale 2, and that unit weight is a float type column. But also note that unit weight has a precision of 53, despite us setting it to 36. This is because when we define a float with precision n, SQL Server treats n as one of two possible values. If n is between 1 and 24, n is treated as 24, and if n is between 25 and 53, n is treated as 53. So as we can see, even though we have a lot of control over things when we use EF-Core, we are still subject to whatever rules govern the database where we deploy our model. Let's wrap the demo up by just verifying that the name column of the orders table is indeed now a non-nullable nvarchar with length 50, just like we see here. In the demo we saw how we can influence how EF-Core infers our data model by decorating our model classes with attributes. By doing so, we were able to create a model in the database that closely mimics the real-world objects that we were representing in our data model. There are a number of circumstances that govern how we would like to express our data model, such as business rule requirements, which may on their part be governed by requirements to accuracy, regulatory requirements, resource management, etc. There may also be requirements to how data must be presented in a visual layer, such as a graphical user interface or a report that we would like to be reflected at the lowest level of the data model, which in many cases is the database. As with so many things, we must remember that even though we want our data model to reflect our real-world classes, we must be careful not to over-engineer. As we design our data model to closely fit our real world, we must also keep in mind that the data model in the database will be our last layer of flexibility. This means that the more strictly we enforce all the rules and all the characteristics of our real-world model in the database, the more costly changes to these will also be. For example, we might want to set some restrictions on decimal types as we did in the demo. If we set up our decimals to have a scale of 2, meaning 2 digits after the decimal point, this has permanent implications. All decimals stored while this setting is in place will have 2 digits after the decimal point, and further precision will be lost. If in the future we change the data type so it has 4 digits after the decimal point, only values stored thereafter will have that increased scale. Decimals that were stored before will just have 0 for the additional digits. Likewise, if we decide to change something from an invarchar type to an integer, that might not be so easy and could involve a lot of casting of types, which might be much easier to implement in code rather than in the database. In general, our C# code is much more flexible and forgiving of change. Also note that all the things that we just implemented using attributes could also have been implemented using AFCore's Fluent API. It is of course a matter of preference how we implement such restrictions as we saw in the demo, but as we saw, using attributes requires us to change our model classes. This may be seen as polluting these classes in an unnecessary way, and it might not always be possible for us to do so because in some cases we will not have access to modifying the classes directly.